Good afternoon, all of you. Welcome back to the online sessions on AWP. In the last class, we discussed about various loop antennas, okay, and such as circular loop antenna, rectangular loop antenna, triangular loop antenna, helical antennas. And in today's session, we try to go with the radiation characteristics of the loop antenna. Right. Earlier, before our examinations, before our internal examinations, we discussed about the dipole antenna radiation characteristics, where we found out the electrical field equation and magnetic field equations, that is E theta and H phi equations. And here also similar to that, we have to find out the E theta and H phi equations, which are basically known as the electric and magnetic field wave equations. So we know the EM wave is nothing but an electromagnetic wave generated due to the electric as well as magnetic field. So, and we know that the EM wave is always going to propagate perpendicular to the direction of the electric and the magnetic field. So therefore, to say that an EM wave is being generated, you have to compulsorily derive the equations for electric field and the magnetic field. So if you consider the, say, coordinate system such as a spherical coordinate system, then we normally going to find out E theta, H phi, or E phi and H theta like this. So based on these two equations, we say that an EM wave is being generated or being propagating in the free space. So now let us define the basic definition of a loop antenna. What is basically a loop antenna? A loop antenna is nothing but a radiating coil of one or more turns carrying the RF current is known as a loop antenna. That means it is something like a, imagine that it is nothing but a copper wire. So this, if you simply wound a copper wire like this, we normally going to simply form a loop antenna. So the wounding can be done by in a circular fashion. It can be done in a rectangular fashion. It can be done in a triangular fashion. It can be done in a square. It can be done in a hexagonal fashion. So accordingly, we'll be getting the appropriate shape of the antenna. So whatever may be the loop antenna it is, whatever may be the shape of the antenna it is, what is the main purpose of this particular antenna? It has to radiate the EM wave, radiate the EM field waves. Now here we may have one turn or we may have more than one turns. So this is what basically, that means a simple wire will be taken, and that wire is normally going to get wounded to form a loop antenna. So it is going to be very simple antenna, normally used at a frequency range of 300 megahertz to 3 gigahertz range frequencies, which is basically known as the UHF range of frequencies. And the current through this loop antenna will be always in phase. So the entire current will be in phase with this particular loop antenna. Okay. So these are the basic features of this particular loop antenna, where the current is going to be in phase and the frequency range is going to be 300 megahertz to 3 gigahertz. So in the syllabus, we have two types of antennas, loop antennas. One is small loop antenna, another one is going to be a large loop antenna. So this small loop antenna, large loop antenna are differentiated based on the circumference of this particular loop antenna. Now this entire circumference, that means if you find out the circumference of this particular shape, circular shape or rectangular shape, triangular shape, will be normally differentiate based on the circumference of the antenna with respect to the wavelength of the wave that we normally going to propagate. So if you normally going to take a circumference which is less than lambda by 10, what does it mean now? It is something like less than lambda. If circumference of the loop antenna is less than lambda, so I may take lambda by 10, lambda by 4, whatever it is, then it simply comes under the small loop antennas. If the circumference of the antenna is comparable to the wavelength of the wave that we are propagating, then it is simply known as the large loop type of the antennas. So now these two are basically divided based on the electrical properties of the two antennas. Okay. Now let us look into the basic loop antenna construction on the coordinate system. So if you imagine that as rectangular coordinate system, if you imagine rectangular coordinate system, and we normally going to place a circular loop antenna like this, where this is nothing but origin of this particular coordinate system, as well as center of the loop antenna, circular loop antenna. And R and A both are going to be same, which is nothing but equal to radius of this particular circular loop antenna. So if the total circumference is less than wavelength, that is C is less than lambda by 10 or lambda, then the antenna is simply going to be electrically called as electrically small. So the current within the loop can be approximately taken as constant, so which is considered for the electrically small. So if the current which is taken flowing through the loop antenna is going to be as constant, then we can say that this particular antenna comes under the loop antenna, small loop antennas. And other design parameters for the loop antennas is going to be the radius A. The radius A of a circular loop antenna is going to be less than 0.03 lambda, and circumference is less than lambda by 5. Already we discussed this parameter C. And one more parameter that is called radius of the circular loop antenna, it will be taken as less than 0.03 lambda. So these two are the design parameters for the small loop antennas. Now let us look into the expression for the radiation characteristics of a loop antenna. Now here we are simply considering the spherical coordinate system. What is a spherical coordinate system? Basically going to have the coordinates. The coordinates are going to be simply r, theta and phi. R phi and theta and phi are the basic coordinates of this particular circular coordinate system. So now when you consider that such a coordinate system, we normally expect the electric and magnetic fields are say propagating along the phi direction. If electric field is propagating along phi direction, then the magnetic field will be propagating along the theta direction, because the phi and theta are always going to be perpendicular to each other in the spherical coordinate system. So by virtue of nature, if you generate electric field, magnetic field will also going to get generated. If you generate electric field by virtue of nature, electric field in turn is simply going to get generated. So that means we need to generate either one of these two generate the in order to generate the EM wave. Okay. So now to generate EM wave, the electric field and magnetic field are a must. So if you generate one by the what is that by the properties of the Maxwell's equations, other field is automatically going to get generated. Okay. So that's what the Maxwell's 3 and 4 equations. Based on the Maxwell's equations, we normally going to say that if you generate electric field, magnetic field in turn will be induced. If you generate magnetic field, electric field is normally going to get induced. So that is based on that, what we can say now, we can simply say that based on that, the electric field say in the direction phi, if electric field in the direction of v phi, then definitely magnetic field will be in the direction of theta. So based on that, we can just simply designate these two vector quantities. Now for simplification purpose, what we'll do now, we will be simply considering the vector quantities. Okay, just to simplify our equations, we only consider vector representation, and we solve for the vector representation. And after we solve, we simply apply it for the appropriate coordinate system. So circular loop is approximated. Now for simplification purpose, once again, this circular loop is simply approximated to dual of the dipole antenna. So already we discussed about a dipole antenna. In the earlier sessions, where we have developed the equations for E theta and H phi. So we'll be using the same equation here also. So just to simplify our working, just to simplify our derivative part, what we're doing is we are simply considering this is going to be two dipole antennas, and they are interconnected. So they are interconnected. So therefore the circular loop is approximated to dual of the dipole antenna. So it's going to be like a two dipole antennas are interconnected. So circular loop antenna is considered to be a two dipole antennas which are interconnected for a simplification purpose. Now, after we do this, now what is another assumption we are normally going to have? This length L is always going to be constant, which is going to be equal to radius of the circle. So under that consideration, we proceed further. So here we have to find out the E phi and H theta expressions in the far field region. So in the far field region, so we always write the equations for the far field region. We don't really look into the near field region equations. Now another, we are assuming that let the wave is propagating in the z direction. If the wave is propagating in z direction, so electric and magnetic fields will be along these two directions. That is how we can normally going to consider. So we consider like this. Now let this A is equal to D, where A is nothing but radius of the circle, and D is going to be the distance between these 2 points A and B, or B and C, or A and D, so like that, so on and so forth. So E phi I can write as equal to the component E phi, that means electric field is normally going to flow along these two dipoles. So therefore, we have to consider the electric field flowing through these two dipoles. That is, A to D is one dipole, BC is another dipole. So therefore, field components in A to D direction has to be considered, and the field components from B to C has to be considered. If B to C direction is the reference direction, then what we can have is, we can simply write it like this: E naught. E naught is the vector quantity of the electric field. So this E naught is taken as minus E naught with respect to this. So if it is the positive direction, we consider e power minus j xi by 2. Now this xi by 2 is nothing but phase, total phase. This xi by 2 is nothing but the total phase. Now xi is known as the total phase difference. Xi is nothing but total phase difference. Now this total phase difference concept we discuss when we deal with antenna arrays, where we derive the equation for the total phase difference. Now with the basics of the wave representation, we can represent the electric field as E naught into e power j xi by 2, where xi is the total phase difference. Okay, this minus is normally going to designate that the wave is propagating in the positive direction. So when it comes to be negative direction, we normally going to consider this as plus, e power plus, and the phase is normally going to be opposite phase with respect to this. Therefore, I can write this as minus e naught of e power j xi by 2 plus e naught of e power minus j xi by 2. Now, what is the expression for xi and all for total phase difference? We discuss this basic equation when we deal with the antenna arrays. For a dual dipole antenna, we have two antennas connected in a dual dipole antenna. There we discuss about this particular dual dipole antenna. Okay. Now, next is, we just simply derive this equation now as if E phi is equal to E naught, if I take common, minus e power plus j xi by 2 plus e power minus j xi by 2, all this I can write. Now if I take minus e naught as common, then I'll be getting this in the form of e power j theta minus e power minus j theta by 2j, which is equal to sine theta. Now we already know that it is this equation is nothing but equal to sine theta. So therefore, this equation I can write as equal to e power j theta minus e power minus j theta is equal to, I can write this as 2j sine theta. So by expanding this in this format, I can write this as e naught into 2j sine xi by 2. In place of theta, we have a xi by 2. So we can write this as xi by 2. Now, we can write this xi, which is nothing but the total phase difference, is equal to beta d cos 90 minus theta. So just remember this equation. We'll derive this equation when we deal with the array of antennas. Okay. So until that time, please remember this equation. And anyway, we have to remember this equation in case of problems also in the AWP subject. So therefore, please remember this formula. So this xi is equal to, I can write is beta d cos of 90 minus theta. What is cos 90 minus theta? It is nothing but sine theta. What is beta? Beta is nothing but phase shift constant. I can write this as 2 pi by beta. From the previous knowledge, we know that beta is equal to 2 pi by beta. 2 pi by beta, that is a formula which you have to replace. Now from the dual dipole antenna, we can write E naught is equal to j60 pi IL by lambda IM. So this is the equation also we should remember. So we'll derive this equation when it comes to the dual dipole antenna in antenna arrays. Okay, array means what? What is array? Array of antenna means what? More than one antenna is connected in array fashion. That means, say for example, if you are dealing with a what is this dipole antenna, you connect more than one dipole antenna in an array fashion. It becomes a array antenna, right? So similar to that, any number of antennas, if you connect them in a array fashion, in a sequential fashion, in a serial fashion, then we can simply call it as a antenna array. Okay. Now let us substitute this E naught equation in this E phi equation. So E phi is equal to minus 2j. Instead of E naught, I can write this as j60 pi IL by lambda A. Then next one, I am going to have sin xi by 2. This sin xi by 2 I can write as equal to what I can write this as. Now we'll be dealing with a small total phase differences. So therefore, for small total phase differences, sin xi by 2 is equal to xi by 2. So which we can replace. Now once we replace this, I can write this as equal to xi by 2. So therefore, this xi by 2 is equal to beta d. What is xi actually? Xi is equal to beta d sine theta. If I divide it by 2, I will divide it by 2 here also. So therefore, I can replace this as beta d sine theta by 2. So these two will get cancelled. I'll be getting this equation minus j square and all. What is minus j square? It will be equal to plus 1. So I can just replace this minus j square by plus 1. So plus 1 into 60 pi I LBDL sine theta by lambda A. So this is the equation I can normally go into form. Now, finally, I'll be replacing the value expression for beta. Finally, I'll be replacing for beta 2 pi by, finally, I'll be replacing this, sorry, this is 2 pi by lambda. I'm sorry, this beta is equal to 2 pi by lambda. So therefore, we replace this beta is equal to 2 pi by lambda. Once we replace it by 2 pi by lambda, we'll be getting 2 into 60, that is 120, pi into pi square, I sine theta by lambda square A. Okay, so this A also I replace. This A is nothing but L into D. L into D is nothing but is equal to area, total area accumulated by the loop antenna. So I can call this as area of the loop antenna as A. And the electric field is always represented in volts per meter. So I can represent it as volts per meter. Now, in order to get the value in terms of magnetic field component, we normally use the intrinsic standoff ratio, which is equal to E by H. So E phi by H theta. Now these E and H should be components which are there along the perpendicular axis, because these two are orthogonal to each other. Since these two are orthogonal to each other, we have to use the orthogonal components here. So eta is equal to E phi by H theta, which is equal to 120 pi. So now this can also be written as equal to 377 ohms. Now H theta I can write as equal to E phi by eta. So eta is nothing but equal to 120 pi. Right, from the transmission line theory, we can write using EMTL concepts. We can write this, replace it 120 pi, and next E theta I can write as equal to as this equation E theta by 120 pi, all this, and finally I'll be getting H theta is equal to pi I sine theta A by lambda square A. Now always the magnetic field is normally represented in terms of amperes per meter. So these two are the electric and magnetic field wave equations. So once these two are been generated, we can say that EM wave has been generated. Okay. So EM wave is generated based on E phi and H theta. Now EM wave is always going to propagate through a plane which is perpendicular to the plane of H theta and E phi. Plane of H theta and plane of E phi. So this is how the EM wave is going to get propagated, which we already know. Then finally we have to find out the total power dissipated in the loop antenna and also the radiation resistance. Just like in a dipole antenna, we need to derive the equations for these two. So therefore the total power radiated is nothing but equal to the surface integral of the average power radiated. So if you integrate the power radiated over the entire surface, why it is going to be surface? Because we are going to consider the complete plane. Since we are considering the complete plane, we have to consider the surface. So therefore we normally apply the surface integral here. Surface integral means we normally going to use two integrations. Volume integration means three integrations. Line integration means one integration. So we already know that with the basics of the EMTL subject. So therefore we can write omega is equal to like something like double integration. Now one integration is going to vary for theta, another one is going to vary for phi. So theta is going to vary between 0 to pi, we know. Phi is also phi is going to vary between 0 to 2 pi. So PR, what this is nothing but a differential surface. So the differential surface I can write as equal to r square sine theta d theta d phi in a spherical coordinate system. So this is also, this equation we have derived simply from the basics of the coordinate system. Okay, so next is this PR is nothing but the average power radiated. So what is the average power we can write in terms of the vector components? It is going to be half E phi H theta. That is basically the expression for the average power radiated. Okay, so from the basics of electrical technology, we can write this average power is equal to half E phi H theta. Okay, now we have to solve for this now. So first of all, we solve for d phi. So integration of d phi is nothing but phi we normally have over the limit 0 to 2 pi. When you apply for 0 to 2 pi limits, r is replaced with a here. So that's why I can write this as a square, and this is going to be 2 pi minus 0 is 2 pi. So 2 pi I'll be having 2 is going to get cancelled, and finally I'll be simply getting this equation as something like this. Okay, and here I'm replacing this e phi and h theta. So once after I replace e phi and h theta, I'll be finally getting into this particular form. Okay, so now I'm simply separating out all the constants with respect to theta. So whichever is the theta, only the theta is simply brought it over here. Now for simplification purpose, we consider the even function here. So if you consider even function, I can just take this as 2 integration of 0 to pi by 2 sine cube theta d theta. Now by solving this integration of sine cube theta, we'll be getting 2 by 3. So now by solving this 3 will go 4 times. So it will be 40 pi to the power 4 I square a square by lambda to the lambda to the power 4. All this equation I'll be getting. Okay. So finally I'll be getting the equation for the total power radiated is equal to 160 pi to the power 4 Im square a by lambda square whole square omega by m. So this is what watts per meters. So this is the equation for the total power radiated by a loop antenna. So in the exam, he'll ask us derive the expression for the power radiated for the loop antenna, total power radiated for the loop antenna. Then you should derive this complete equation for the power radiated for the loop antenna. The next one is the radiation resistance. Now, when it comes to the radiation resistance, what is basically power? Power is equal to IRMS square into R, basic formula we know. So this power, total power I can represent as is equal to W in the previous discussion what we have just now. So is equal to IRMS square into R is nothing but the radiated resistance. So I can take this as RR. Now we know from the electrical technology, the IRMS square, the IRMS value of the current is equal to Im by root 2. Im by root 2. So we got omega is equal to 160 pi to the power 4 Im square a by lambda square whole square, which is going to be watts per meter. So omega is equal to 160 pi to the power 4. Now what is Im? Im I can replace as going to be root 2 times IRMS from this equation. So I can replace Im as root 2 IRMS whole square. Then I'll be solving this equation for this. Now once if I solve this equation, I'll be getting this entire thing over here. Then pi I can replace this pi is equal to 3.14 as you know. So replace pi is equal to this. Then finally you'll be getting the radiation resistance of a loop antenna is equal to 31200 a by lambda square whole square. So this is going to be the radiation resistance equation of a loop antenna. So in the previous classes, we discussed about the radiation resistance of a half wave dipole antenna, which we got it as 73 ohms. Okay, so here we got this particular basic equation for this. Then next, right now. So by further, we can also represent the for a single loop antennas, the radiation resistance is equal to 20 pi square c by lambda to the power 4. So in terms of the velocity of light also we can represent. Okay, these two formulas we can use, but better we use the radiation resistance RR because this we have in the syllabus where we derive the equation entirely. So this is the direct equation which we can remember, using which also we can solve the problems. Okay. So if it is going to be for a single loop antenna, then we are going to have A. If it is going to be for more than one loop, then we normally replace this A by NA. So this NA is going to be for n number of turns of the antenna. Okay. So please replace this A by NA here so that we can represent it as n times A. So which resembles the n number of turns for the antennas. The next one is going to be the advantages. What are the basic advantages which we normally encounter for the loop antennas? The basic advantages of loop antennas are going to be compact in size, right? And they are obviously they are just made up with a simple copper and aluminum wire. So therefore, it's going to be very cost effective, low cost. It will be, and it will be versatile. Versatile means what? You can simply use it in many applications. What are the major drawbacks of this? It is going to have poor impedance matching. Okay, so therefore, wherever we have a problem of impedance matching, we normally going to use this kind of antennas. Then it is normally going to have a very high resonance effect. So these are the drawbacks of this loop antennas. And finally, the applications where we normally use this loop antennas. We normally use these loop antennas for medium frequencies, high frequencies, short wave receivers. And we also use this in RFID devices, radio frequency RFID tag devices. Then it is normally we normally use these antennas in the UHF transmitters and receivers. So example of this is normally in the olden days we are going to have a mobile pages. So that means in 2000 or before 2000 we used to have a mobile phone only for voice communication. In order to transmit a message, people are going to use the mobile pages. They'll be having individually they'll be having a pager device. Using the pager device they're normally going to exchange their voice information, they exchange the data information. So next one is going to be NFC antennas. Okay, so these are the basic applications where we normally going to use this particular type of the loop antennas. In the next class, we go with the helical antenna in depth, and we discuss about the basic mathematical part of the helical antenna. Okay, so after that we compare various antennas with respect to the far field region. Thank you very much for the today's session.